Logic circuits. Propositional logic can be applied to the design of computer hardware. This was first observed in 1938 by Claude Shannon in his MIT master's thesis. Logic circuit is an electronic circuit having one or more inputs and only one output. The relationship between the input and output is based on a certain logic. Hence, logic gates are named as AND gate, OR gate, and NOT gate. A logic circuit or digital circuit receives input signals, say P1, P2, up to Pn, each a bit, either 0 or off, or 1 or on, and produces output signals S1, S2, up to Sn, each a bit. Now let's look at the basic logic gates. We have the inverter, or this is the NOT gate. And this is the illustration for the NOT gate. A triangle with a circle on the tip, at the tip. Next, we have the AND gate. So we have this. And we have the OR gate. Okay, and of course, take note of the symbols on this right side. These are from our logic propositions. So we have this notation for AND, this for negation, and this notation for OR. So let's have this. If we have an input 0 or off, the output is 1 or on. If it is on, then the negation is off. Now let's go to OR gate. So if we have on signals, so 2 on signals or 1, so the output is also on or 1. Okay, take note when we talk about OR in our proposition, the truth value for OR, it is always true if one of the propositions is true. Or in this case, if one of the signals is 1, so the output is 1. So next we have 1 and 0. So one of the signals is 1, so therefore the output is 1. Next, what if we have this 0 and 1? So again, one of the signals is 1, so the output is 1. And last, if both are 0 or off, then of course the output is off, so we have no output. Let's go to the AND gate. So when we say AND, when we go back to our logic, if both propositions are true, then that's the only time that the whole statement is true. Otherwise, it is false. So in this case, if both signals are 1 or on, then the output is on or 1. Otherwise, it is off or 0. So in this case, this is the only output with 1 or which is on. The rest is 0. Now next, find the output of this combinatorial circuit. So we are given with P, Q, and R. We have these 3 signals. Now to solve this, so let's remember these 3 gates. These 3. Okay. So first, take note that this symbol is for NOT or inverter for the NOT gate. So therefore, this Q signal will become NOT Q. This R will become NOT R. Next, we have this operator or gate. This gate is for the AND. So therefore, the 2 signals connected here are P and NOT Q. Okay, so therefore, we can write this as P and, so this is the symbol for AND. Then we have NOT Q. Last, we have the last gate. the OR gate. So this is the OR gate. So we have two signals for this. We have this first group, P or not P and not Q, and then we have this not R. So therefore, we have this final output. Okay, so you just use parentheses for this group. Okay, now what if we have these values? 1, 1, 0. So not Q, so 1 will become 0 or off, and this 0 will become 1. Now for this gate, this is P and not Q, so we have 1 and 0, so this is 0. Okay, it is off. And last gate, we have 0 or 1, so it is OR, so if one of the signal is 1, therefore the answer or the output is 1. So we have an output here. It is on. Okay, we have these two examples, so you may pause the video if you want to try this one. Find the output of each of these combinatorial circuits. So for letter A, let's examine letter A. So we have three signals, P, Q, and R. So let's start with the first gate. We have the NOT gate. So R will become not R. Then this is an OR gate. So we have Q or not R. So Q or not R. Then this is an AND gate. So we have two signals. We have P and this group. So since this is a group, so we need to use a parenthesis. So this will become P and this group or this signal. And last, this is an inverter, so we'll just negate this. So we have this negation of this whole expression. So therefore, this is the output of this combinatorial circuit. Now, what if we have this? So this is 1, actually, P is equal to 1. So we have this 1, not R, so this is 0 or off. Then for this logic gate, we have 1 or 0. So this is OR, so this is 1. The output is 1 here. Next, this is AND. So we have 1 and 1. So this is 1. And last, for the output, this is the negation of 1. So 0. So there's no output, so 0. It's off. Now let's go to B. We have these three signals, P, Q, and we have R. So we have this P will become not P, Q will become not Q, because this is a negation gate or the NOT gate, the inverter. Next, this is AND, so we have not P and not Q. Now below, for this gate, this is also an AND gate, so we have P and R. So for our final gate, this is OR. So we'll just need to use parentheses to group these expressions. So we have this, and the operation is OR. So this is now the output of this logic's combinatorial circuit. Okay, so what if we have these values? P and Q are 0 and R is equal to 1. So let's start here. This is not P and not Q, so the negation is 1, 1. So next operation or logic gate is AND. So 1 and 1 is 1. Then below, 0 and 1 is 0. And last, this is OR. 1 or 0, 1. So it is on. Okay, so you may practice this. Find the output of each of these combinatorial circuits and then try finding its exact output with signals P and Q given. Okay, so we have these answers. So you may compare your answers to these answers. And we have this. Okay. So exercise. Build a digital circuit that produces the output, this one, when given input bits P, Q, and R. So take note, we have two groups here. This is the main operator. So we'll group P, R, and then we have P, Q, and R. So here, so we have P, R, and then we have P, Q, R. So we'll start here at the left side. So this is not R. Of course, we cannot do the operation OR without first finding the negation of R. Okay, so next is we can now use the operator OR. So we have this drawing, P or not R. So we're done with this first group. Now next, let's go to this first group, a second group, I mean. So take note that for this second group, we have a subgroup for this one, the inner group. So we'll start here. So again, we cannot use the OR group without finding the negation of R. Okay, so we have this. Then the next we have this OR. So we have Q or not R. The next operator, we have the negation. We cannot use this OR without negating P. So we will negate P first. Okay, and then we can now have this operator OR. So curve. Okay, so this is the drawing. And then last, we have this major operator. We have the AND. So AND straight, it's not curve. So we use the straight edge. So therefore, this is the logic circuit. So last, construct a combinatorial circuit using inverters OR gates and AND gates that produces this output or the output from inputs B, Q, and R. So by just looking at this is the main operator. So we have two groups, this one and this one. So we have P, R, not Q, P, R, Q, and the second group is P, Q, R. So let's start here first. So we can actually negate them first. So negate. Then we have the inner operator. So this is now, we're done with negation. So we can now have this OR. Okay, so OR, this is OR, not P or not R. Next, we can have this now AND. So we have this Q and this group. So we have this. So meaning we are done with this first group. Now let's go to the second group. We have Q or R. Or first, we have this, not P. And then we have Q or R. Then we have this operator AND. So straight edge. So meaning we're done with this second group. So last, we have the major gate or operator. We have the OR. So curve. So therefore, this is the combinatorial circuit. Thanks for watching. I hope you learned something.